Okay, so let's proceed with our run intelligent controller topic. The topics prepared by Dr. Jocelyn Reyes are here. So it's a review of the ORAN architecture. We already completed this in our first session. And then what we will do today is the RIC overview and the functional split, run control loops, the R apps, the X apps, the non-real-time RIC framework, and the near real-time RIC framework. Okay. Okay. So I'll try to cover it before the time of 12 p.m. before 12 p.m. Okay, so let's start with the RIC overview and functional split. If you look at the ORAN working groups, so as mentioned last time, there are 11 working groups in the ORAN Alliance that are focusing on different parts of ORAN architecture. Okay, so in this case, in the overall architecture and use cases is taken care of the work group 1. Now talking about the run intelligent controller, so the non-real-time RIC and the A1 interface and the near real-time RIC plus the E2 interface are being handled by the work group 2 and the work group 3. Okay. And the other work groups are here, including 7, 6, 7, 8, 9, 10, 11. Okay. So for the run intelligent controller, it's work group 2 and work group 3. Okay. So what is a run intelligent controller? So since 5G applications, some of the applications, particularly the URLLC, require low latency. And then 5G specifications require the network function virtualization and software-defined networking to enable configuration, optimization, and control of RAN infrastructure, especially at the edge of the network. The RAN intelligent controller enables the eNode B and the gNode B functionalities for what we so-called the network intelligence. Okay, resource assurance and resource control. So originally defined for 5G Open RAN, okay, the RIC, and essential to support interoperability of different hardware. Okay, that's why it's available only as of now in the Open RAN architecture, the RAN intelligent controller. So it can support the interoperability of different hardware and software components. And it also leverages data analytics and AI platform for better resource management. And then some optimization applications include, as Johnson shared to us a while ago, the QoS, slicing, and mobility. And in terms of self-optimization, it's very efficient. Okay, so very efficient because it has a feedback mechanism. It can tweak the parameters we need based on the policy that is set by the operator to meet the required thresholds or values. So let's compare what's the difference between the non-real-time RIC and the near real-time RIC. Okay, so the non-real-time RIC, this is located at the SMO framework. Okay. And the near real-time RIC is, it's separately in the near real-time RIC. And then NRT or the non-real-time RIC, it supports tasks that require greater than 1 second latency. And then host are apps for run automation, optimization, such as the configuration management and data analytics. So there are apps, we call it R apps inside the non-real-time RIC. And when you compare it to near real-time RIC, near real-time RIC supports tasks that require less than 1 second in latency. Okay, because it's giving down the parameter change, okay, thresholds down to the E2 nodes. So it should be near real-time. It's not real time, but it's near real time. And it hosts the X apps for eNode B, GNode B functionalities such as radio resource management. So there's a lot of X apps already. No? So as you saw in the previous discussion, there's traffic steering, which is the equivalent of load balancing right now. There are also network slicing. Okay. There are also power saving, which there's also equivalent feature right now, the power saving feature. Okay. So I saw also different applications and different vendors um, developing those kind of software and applications. So there is one vendor that they're developing this software, also powered by artificial intelligence, but working in the traditional network. So what they're doing is that they're tapping into the OSS, the EMS, okay, of the current vendors, and then tweaking the parameters of the features and the power saving. Okay. And currently, right now, I think there is a limitation only on the specific features because vendors do not specifically open those features to other third-party vendors, right? Of course, to protect also the business. Okay, so so this is the main difference of the two. Okay, so going to the non-real-time rig, non-real-time rig is located here inside the SMO. And work group 2 is the one responsible for the non-real-time rig and the A1 interface. So this part. Okay, so the A1 interface is the interconnection between the near real-time rig and the non-real-time rig. Okay. Now let's go to near real-time rig architecture. For the near real-time rig architecture, so it's composed of the O1 termination. Okay, so it handles the interface between the non-real-time rig to the SMO going to the near real-time rig. A1 termination is connected to the A1 interface going to the near real-time rig. Okay, and inside this near real-time rig, there are apps or microservices that we called XApps. Okay. So XApp is just imagine it like if you have a smartphone right now, just to make it simpler, no? You have the applications. Okay, so you have an application to clean your random access memory. Okay. You have applications to launch some videos. Then you have some applications to handle such tasks, like for example, banking. But for the near real-time rig, so there are applications that handles how to save power. Okay. There are applications how to manage network slices. And there are applications that balances the traffic of the network. So it depends on the applications that the operator wants to trigger. And these applications or XApps are also produced or delivered by different third-party vendors. Okay, that's the beauty of this architecture. So if you don't like the performance of one app, you can just change it to other third application vendor. Just like the app that you're using in your phone. No, if there's a filter, a photo filter that you don't like, and then you found something that is better than that app, you can just change it. Okay, if it makes you more handsome or more beautiful or more um, uh, more glassy skin, better to change the X app. Okay, that's the beauty. Okay, so this X apps, this architecture is being managed by or handled by the work group 3. Okay, including the E2 interface. Okay. Okay. Now let's quickly move on to the split model. No? Okay, so functional split. So earlier we discussed about this split. Okay, so the BBU is split into two: the distributed unit and the centralized unit. And each unit is divided into different protocols. Okay, okay. Um, are apps and X apps already commercially available? Yeah, I saw some vendors, particular Remedo Labs, and I think this Viavi also. They are offering these X apps in different companies. Okay. Mm, so those are the splitting of the functionalities, no? So if you check the 3GPP approach, so how they divide it, so the BBU is divided into two, okay? The CU and the DU, and the RU is still the same, but the functionality or the protocols were also separated. So what is a functional split in 5G? So why is it important? No? What are the three factors that influence the split choice? Different protocol layers will reside in different components. Okay. And the split implementations are more flexible and easier to fit to specific deployments constraints. And the standardization of the splits enables the use of solutions from different vendors. So there are three factors that influence the split choice. First is the specific QoS per service. Okay, so there are services that requires instant responses from the network. There are services that do not require time sensitive services. Okay, so it depends on the specific QoS. Number of users in a specific area. So user density. So some areas have a lot of traffic that congest the network, or some areas have few population but requires heavy data usage. So it depends on the user density. And of course, transport networks. So there are, especially if the sites and the components are geographically separated into each other, that will require a large cost in the transport network. So these are the different uh, factors. Okay. Um, let's see the functional split overview. So we have this monolithic run where the BBU, where it's composed of BBU mainly and the RRU or the radio unit. And then there is what we call the run functional split. So the BBU is split into two: the CU and the DU. Okay. And there are two types of split. We are three types now. So we have the lower layer split, the LLS, the low layer split, and the high layer split. Okay. HLS, and the dual split. It's a combination of the low layer and the high layer. So let's see, the different layer. Like for example, the high layer split. So if you have the functionality of the BBU, or like for example the CU or the DU, you split the functionality into this. Okay. So what happened is that in the CU, okay, in the option one, you can get the RRC or SDAP in the CU, in the centralized unit, while the PDCP, RLC, MAC, and physical and RF is here. And you can also have the option two. For option two, where the split is happening is that the RRC, SDAP, and the PDCP are located in the centralized unit. Okay, so this is an example of high layer split. Low layer split is splitting, the components here, the functionality here in the lower part, in the layer one. No? Okay, so there is a high physical layer and low physical layer. Okay, so if you have this data, so you have the option 8. So this is where the split is happening. Okay, so here inside the CUDU, the high and the low. And in the option 7, You can see that the high physical uh, split is happening in the CU and DU, and the low physical is here in the RU. And the option 6, okay, is happening here. So this option 6 is being implemented in the indoor IBS. The option 7 is for the Open RAN, 4G and 5G, and option 8 is for 2G or 3G. Okay, for the simplicity. Okay, so as I mentioned, this option 6 is being implemented in the IBS, no, or small cells, particularly to femtocells, picocells, and microcells. Okay, and option 7 is preferred for delay-sensitive services. It allows sharing of pool while maintaining low processing on the DU and the RU, and good at the option for distributed RAN deploying massive MIMO. Okay, option 7. So this is uses as easy pre front hole interface by the ORAN. Okay. So if you look at the functional split, the low physical and the high physical, so this is how the split is happening. So we have the split 7.3, this is under 3GPP. Okay. Split 7.2, currently the 5G CPRI, they just use the split option. And the split 7.2x and the split 7.1. Okay, so if you say split 7, so you can see, you can just imagine two box, no? So one box here, the D, and your RU is here. Okay, so meaning the scrambling, the rate matching, the code blocking, the cyclic redundancy checking, attachment is done in the DU, and here is in the RU. Okay, so if it's split option 2, what will happen is here. Okay, so it's a matter of deciding where are those protocols or functionalities will be grouped. No, yeah. So it depends on the applications where to deploy. No? So in the ORAN, we are using this 7.2x. Okay. Okay, here. This one. Okay, 7.2x meaning there is a subgroup again, no? Where we separate this functionality furthermore. Okay. Okay. So that's for the split functionality. Now we'll go to the run control loops. Okay, for the run control loops. So going back to the comparison between the 3GPP and the ORAN Alliance. So as you can see, there is a core network, the CU, the DU, and the RU. For the ORAN, you have the SMO, the non-real-time RIC, the OCUs, the CU, and the ODU, and the RU. Actually, what's happening here, if you are correlating, no, this 3GPP, something like this, no, you are connected. I'm sorry. Probably there is another slide here. Okay. So this one pala, no? This one is connected to the core network. Yan. Yung core network natin. Yan. Okay. Yan. So this is how we do it. Of course, there's a interconnection here, no? Para sa control. Yan. Okay. And then let's see the control loops, no? So there are different control loops located in this architecture. So you can see the different interfaces, and connections to different components. And then there are control loops, and there are also ODU scheduler control loop. So there are what we call the non-real-time RIC control loop mechanism. There are also the near real-time RIC control loop and the ODU scheduler control loop. So it's giving feedback no to the SMO and to the near real-time RIC. Okay, so it's just an interface table with a description and also for the what specification no it's being done. So going back to the control loop no? So I was looking for the slide of explaining the control loops, but I cannot see the slides yet. The specific slide. Probably on the next slide. So, okay, we'll get back that on the next slide. Now let's move on to the R apps and X apps. Okay. So another comparison. So R apps greater than 1 second latency, X app less than 1 second latency. Okay. It's independent of the non-real-time rate. This one is near real-time rate. So the R apps are value-added microservices. Okay, value-added microservices to support and facilitate the run optimization and operation, such as the policy guidance, okay, enrichment information, configuration management, and data analytics. Okay, so microservices, XApps, it can be used to perform radio resource management, RRM, through standardized interface and service models. So the R apps particularly have some examples like traffic forecasts, okay, artificial intelligence, and machine learning model. While the X apps perform these microservices like network slicing, power saving, load traffic steering, okay, and other services. Okay, and both may be provided by third-party vendors. Okay, so let's see some examples of the R app. So this is an example of R app. R app R, which is an RF signal predictor. So what it does is that O1 measurement, it measures O1 measurements of RF signal experienced by the UE for serving and neighbor cells. Okay, and then measurements for the UE location, just like what the geolocation, as Johnson has mentioned a while ago. And the output of this is the future time prediction of the location of the UE, prediction of the RF signal at the location or serving neighbor. Actually, in more technical terms, we call it the RF fingerprinting. Okay, but it will discuss it in the separate discussion. And then we have this RAPU, the cell utilization predictor. Okay, so cell utilization measurements regarding actual capacity, future time prediction for cell site utilization, and based on the trend. And the QoE, the quality of experience predictor. Okay, so measurements of the UE RF signal. So actual run measurement prediction, measurement of cell site capacity utilization, actual prediction, and it calculates the QoE experienced by a particular UE. Okay. So those are the examples no, of the R apps. For the X apps, this was mentioned earlier. So some of the examples here are measurement campaign X app, okay, automated neighbor relation or ANR X app, and admission control X app, okay. And for some cases, there are virtualized functions for 2G, 3G, RNC, and 4G and 2G gateway, for other vendors. So the use cases, we discussed it already last time, earlier. So it includes the power saving, network slicing, and traffic steering. Okay. So let's see the near real-time RIC architecture. Okay. So for the near real-time RIC architecture, it looks like this. Okay. So this is a high level ORAN, near non-real-time RIC architecture. So if you look at this, it's composed of the other SMO framework functions, the inherent SMO framework functionality. The non-real-time RIC is here. Inside the non-real-time RIC, you can see the non-real-time RIC framework where there are app service exposure functions, inherent non-real-time RIC framework functionalities, okay, and the different functions like policy, E1, machine learning, and termination. Okay, so on top of this non-real-time RIC framework are the R apps, okay, connected by R1, okay, and there is also an SMO internal interface connecting these other SMO functions going to this near real-time RIC. Okay, so each functionality has external termination, no, to external termination sources. But you can also see the A1 termination, a specific block for the near real-time RIC connection using the A1. And for the O1 termination also, and the O2 going to the O cloud. Okay, so this is the non-real-time RIC architecture. And going to the real-time RIC architecture, so it provides the platform for the XApps. So it enables configuration, optimization, decisions for multi-vendor run, and uses AI for intelligent management. Interacts with the non-real-time RIC with the A1 interface and can be deployed as centralized or distributed model. So this is the architecture of the near real-time RIC. Okay. So you can see here the near real-time RIC. So there is an O1 termination connected to the SMO, A1 termination connecting the A1 interface to the non-real-time RIC, and it sits the XApps, different XApps, no? Okay. And also there's a management infrastructure. There's also conflict management, which is really important as part of the near real-time RIC. As mentioned by Johnson a while ago, this one is important one because, like for example, you want to activate power saving XApp and then traffic steering XApp, no. So during the time, if for example, like right now, no, if you activate the power saving feature from 12 midnight going to 3 a.m. If there is traffic that surges, no, during that time, your site will be shut down, no. So it will be conflicting. So there should be a mitigation or a mechanism how this X app will talk to each other, okay, and not to conflict the functionality of each um, app. No? And then we have the radio network information base. Okay, so these are additional information used by the non-real-time RIC, near real-time RIC, no, for these functionalities. And the E2 termination going to the E2 nodes. Okay, so you can deploy it in the distributed manner, or you can also distribute like this. Okay, so these are designed serving 4G and 5G simultaneously. So you have the non-real-time RIC in a centralized manner, and then you have corresponding near real-time RIC, no, for every functionalities like 5G only, 4G and 5G, and then 4G only. You can also have like this distributed near real-time RIC. So it's centralized, no? Okay, so, and then every nodes is connected. E2 nodes are connected to the near real-time RIC. So one physical near real-time RIC consists of one or more logical. Actually, it should be non-real-time RIC. Okay. Yep. So that's the summary of the near real-time RIC and the non-real-time RIC. Okay. So just to summarize what we have discussed today. So the RIC enables the management of radio resources and radio networks, and it enables eNode B, gNode B functionalities for network intelligence, resource assurance, and resource control. And the functional split defines how the run functions assigned to the components. Okay. And the three run control loops are non-real-time RIC, near real-time RIC, and the ODU scheduler control loops. The non-real-time RIC framework supports tasks that require more than 1 second latency, while the near real-time RIC supports tasks less than 1 second latency. The R apps are microservices that facilitate run optimization and operations like configuration management and data analytics. The X apps are microservices that can be used to perform radio resource management. Okay.